Hi everyone. Today I'm going to talk about how to fix an unsound practice at the start of zero-knowledge proofs and verifiable computation. For context, you're a user with a slow machine. You have some input X and a computation F that is too hard for you to solve by yourself. So how are you going to compute it? You outsource it to a fast remote server. The server returns you with an output Y. However, the server might be unreliable or even malicious. And you're left wondering, is Y the correct output of Fx? So you turn to verifiable computation or zero-knowledge proof, which we together refer to as probabilistic proofs. You demand the server to take on the role of a prover, which is that it sends you a proof that Y is indeed the result of Fx. You yourself now becomes the verifier. You check this proof. If the prover behaved, you accept it. Otherwise, you reject with overwhelming probability. Now, probabilistic proofs are becoming more and more popular. They're now the centerpiece of billion-dollar crypto sector, and they're a target of countless research projects. However, despite the hype, we need to first ask ourselves an important question. Are we actually proving the right thing? To demonstrate what I mean by this, let's start with the most basic probabilistic proof framework. People usually start with an implementation of the computation, which is written in some form of a source code. They then translate this implementation into a set of mathematical constraints, which are satisfiable if and only if the prover executes the computation correctly. Now, the prover uses the implementation and the input to produce a satisfying assignment for the constraints, which are then checked in a backend proof protocol where the proving time largely depends on the size of constraints. So naturally, people want to minimize the size of constraints. And what they realize is that since they already have the output from the prover, they can write out some form of a checker which checks that the output is indeed correct according to the implementation. So, as an example, if we want to sort an array A, this checker just needs to specify that the output is indeed a permutation of A and that the output is sorted. This two statement can be translated into far fewer constraints than, say, translating a quicksort or merge sort algorithm. And this is indeed what they did. Instead of translating implementation into constraints, they translate this checker. This usually leads to far fewer constraints being produced, and as a result, faster proving time. Checkers, however, causes a major problem that could undermine the correctness of the entire system, which is that you cannot use the checker to actually find the output. So the prover would still have to rely on the implementations to produce the satisfying assignment, but this time to satisfy the constraints produced by the checker. There's no formal link between the implementation and the checker, which raises a question. Are these people even verifying the same computation? Well, this is indeed our research question. How can we generate efficient checkers for probabilistic proofs while at the same time close this gap between the checker and the implementation? We introduced DeStefano, a systematic procedure for correctly linking the implementation and the checker. We applied DeStefano across our benchmarks, and DeStefano successfully mechanically verified 10 of the 11 checkers we produced. For the remaining checker, we verified using handwritten proof. So, how does DeStefano achieve this? We have to first take a step back to understand what are the exact issues caused by the checker. As stated earlier, there's a gap between the implementation and the checker. This allows a buggy checker to sneak into the system, which may cause two problems. If the buggy checker is too restrictive, then it might be the case that the prover correctly executes the implementation, yet still fails to find a satisfying assignment for the constraints. On the other hand, this buggy checker might be too relaxed, which allows the prover to produce an erroneous output, yet somehow still manages to satisfy the constraints. Both compromises the correctness of the system entirely. So how does DeStefano solve this problem? Well, it does so by building on prior works of refinement. DeStefano applies refinement on both directions between the implementation and the checker, and proves that the checker is indeed an abstraction of the implementation. And as a result, for any given input, the output produced by the implementation will be the same output that will be accepted by this checker. Now, before I showcasing you how refinement works on one of our concrete examples, let me first digress and talk about the constraints that are used in probabilistic proof protocols. These constraints are represented as a set of mathematical equations that needs to be fixed at compile time. What this tells us is that if we want to translate a program into constraints, we need to first unroll all of its loops and embed all of the function calls. Once we've done that, we can largely translate this modified program line by line into our constraints. What this entire process tells us is that the time complexity of the program will be the dominant factor in deciding the size of constraints. If the checker can run asymptotically faster than the implementation, it is almost always guaranteed that it will produce fewer constraints. Now, let's see one of our benchmarks that we used and how we can apply refinement on it. In this benchmark, we are given a set of nodes in two-dimensional space, and we want to find the Convex Hull of the graph. The Convex Hull can be defined using three properties. It needs to be an enclosed shape. It is convex. This means that every angle of this shape should be pointing outwards, away from the cluster of nodes. And finally, it is a hull. This means that every node needs to be light either on this hull or inside the area enclosed by it. We additionally assume that there are at least 3 nodes on this graph, and then those 3 nodes lie on the same line, just for simplicity. And for the graph on the right, we will see that the path A, B, C, D, E, F, A will indeed form the Convex Hull of the graph. Now, for the implementation of the Convex Hull problem, we choose gram scan, which is a popular algorithm that solves this exact problem. There are 2 steps in gram scan. In step 1, we're going to find the bottommost node. Using that as reference, we sort the remaining node in counterclockwise order. Once we obtain this ordering, in step 2, we're going to process these nodes in that order. You can see step 2 in action here. So we elude details of step 2, but you can see that this is a linear algorithm. It processes each node once. And we find Convex Hull at the end of step 2. So the time complexity of gram scan is going to be dominated by the sorting. Sorting is expensive. It is worse than linear. So can we get rid of sorting? Can we come up with an efficient checker that does not require sorting and runs in linear time? Well, how can we check a Convex Hull? It needs to have at least 3 nodes on it. It is convex. This means that if we take a look at any of the nodes on it and the 2 edges connecting to it, they should form an angle pointing outwards, away from the cluster of nodes. And then finally, for any node that is not on the hull, they should be contained in a triangle formed by 3 of the nodes on this hull. In this case, G is contained by ADF, and then H is contained by ABD. You might be wondering, how can the verifier efficiently find this triangle? Well, it can simply ask the prover for it. The prover supplies this triangle, and then we just need to modify this checker so that it also checks that the 3 corners of the triangle are indeed nodes on this hull. And finally, this Convex Hull might be described using a lot of ways. But we want the checker to only accept the exact description produced by gram scan. In this case, this means that the Convex Hull should start with node B and then go in counterclockwise direction. Well, the simple fix for this is that we restrict the checker so that the only output it accepts should have the first 2 nodes matches with the correct output of gram scan. Now we're finally done with the checker. We know that it is indeed linear. We process every node exactly once, and finding the first 3 nodes in gram scan is not going to take more than linear time. This is great. This checker is efficient. It is asymptotically faster than gram scan. So as a result, for a large enough graph, it is guaranteed to produce fewer constraints than gram scan. For many people, this will be the end of line of their work. But as we said earlier, there's still this missing gap. So how can we show that the output produced by gram scan is going to be the same output accepted by the checker? Let's see how DeStefano uses refinement to show us this. As I described briefly earlier, this refinement is bidirectional. In direction 1, And we need to show that everything produced by the implementation is always accepted by the checker. In direction 2, everything accepted by the checker will always be produced by the implementation. Distiller accepts this checker if and only if both refinements are formally established. And we do so by writing them into a verification language called Viper. We then run Viper and Wait, the refinement didn't actually work? Wait, what's going on here? Well, apparently the refinement tells us that the checker can be fooled by something that will never be produced by gram scan. Well, it doesn't tell us what it is, but it gives us enough hint for us to produce it. So what is it? B, C, E, A, D, F, B. What even is this thing? Well, does it have at least 3 nodes? Yes. Are all the angles pointing outwards? Yes. Are all the nodes not only contained in triangles? Also yes. And finally, it does match the first 2 nodes of the correct convex hull. Ha! So this is indeed not a valid checker. For those people who did not use refinement, they might never see this coming. This could be bad. So what's the moral of this story? If you are using a checker, you can be verifying the wrong thing, no matter how careful you are. And as a result, you should always prove the correspondence between the implementation and the checker. And you can do so by using a refinement proof, which we described much more detailedly in our paper. So finally, just to put our work into context, there has been work applying formal methods on the proof protocol itself, on the translation from the checker to the constraints. But we are the first to establish this link between the implementation and the checker. Through using refinement, we close a major gap in probabilistic proof systems, making the whole system a lot more sound and correct. I want to thank my co-authors, Devora, Zach, Mike, and Thomas. And thank you. I'm happy to take any questions.
Okay. Great talk. Do we have any questions? I have one.
I guess a serious question and kind of a frivolous one. The serious question, so in this context, your motivation was verifiable outsourcing. Mm-hmm. And so like questions about proof of knowledge or zero knowledge were not necessarily relevant in that setting, but I'm curious if those properties, ensuring that those properties hold, is covered by your paper.
Yeah, so if you have a proof of knowledge, you're still gonna be using the same framework to some extent. You're still gonna have these constraints, so our verification, our refinement also applies to that as well.
Got you. Okay, cool. And then the frivolous question, how should one fix this particular checker that you told us about?
We just want to find this one thing that you're never going to guess what's going to happen. Like, I didn't even see the counterexample myself the first time, so I think it works really good.
Cool. Thanks.
You have one more question?
Are there higher dimensional extensions of this work that would extend the algorithm that would apply to the multidimensional analog of the gram scan?
You mean convex hull in multi-dimensional?
Let's say 3D, yeah.
Yes, but I think that would be a different problem. I'm not entirely sure if gram scan can do that.
Sure, thanks.
All right, let's speak again.